Preparing for a software engineering at Splunk interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a scalable log ingestion service for Splunk? I would separate ingestion from indexing so each tier scales independently. Stateless collectors accept events, authenticate tenants, apply lightweight parsing, and write batches to a durable queue. Partitioning by tenant and time distributes load while preserving useful ordering. Indexers consume asynchronously, with backpressure protecting downstream systems. Replication prevents data loss, and metrics track lag, rejection rates, and throughput. I would begin with clear delivery guarantees, because exactly once processing can cost significantly more than at least once delivery. While answering, focus on ingestion protocols, partitioning, buffering, backpressure, horizontal scaling, durability, schema handling, tenant isolation, observability, and how you would balance latency, throughput, and storage cost. Question 2. How would you handle duplicate events in a distributed log processing pipeline? Duplicates typically result from producer retries, consumer crashes, or replayed partitions. I would attach a stable event identifier at the source and make downstream writes idempotent using that identifier within a bounded time window. Consumers would checkpoint only after durable processing, then safely replay after failure. Full global deduplication is expensive, so I would document an effectively once guarantee, choose a practical window, and expose duplicate rates for operational visibility. Make sure to cover why duplicates occur, event identifiers, idempotent writes, deduplication windows, checkpointing, retries, retention limits, memory or storage costs, and the difference between exactly once processing and effectively once outcomes. Question 3. What is the difference between a search index and a traditional relational database index? A relational index is usually optimized for structured predicates such as equality, ranges, or joins on known columns. A search index often uses inverted structures mapping terms or fields to documents, making text and event retrieval efficient. Search systems accept more storage and indexing overhead to support flexible queries across large event volumes. I would select based on workload. Relational databases for transactional integrity and joins, specialized search indexes for high-volume exploratory retrieval. In your answer, compare access patterns, inverted indexes, tokenization, structured fields, consistency, update costs, query flexibility, storage overhead, and why observability searches often require specialized indexing strategies. Question 4. How would you optimize a slow query over billions of log events? I would first inspect the query plan and measure scan volume, latency, memory, and network transfer. Then I would narrow the time range, filter on indexed fields early, project-only needed fields, and use partition pruning. Large aggregations may require parallel workers or pre-computed summaries. I would test caching only when query patterns repeat. Finally, I would compare results and resource usage on representative data, because an optimization that helps latency but overloads indexers is incomplete. Be sure to mention query profiling, time range filtering, indexed fields, early filtering, partition pruning, selective projections, aggregation strategies, caching, parallel execution, and validating improvements with realistic production like workloads. Question 5. Explain how you would implement backpressure in a streaming system. Backpressure prevents a fast producer from overwhelming slower consumers. I would use bounded buffers and propagate capacity signals upstream, allowing producers to slow down, batch, or temporarily reject work. Durable queues can absorb short spikes, but retention and disk limits must be explicit. Retries need exponential backoff and dead letter handling to avoid retry storms. I would monitor queue depth, processing lag, rejection rate, and saturation, then define an operational policy for graceful degradation. Focus on bounded queues, producer throttling, consumer capacity, rate limits, retry behavior, overload signals, dead letter handling, graceful degradation, monitoring, and avoiding unbounded memory growth during traffic spikes. Question 6. How would you design a highly available metadata service? I would replicate metadata across failure domains and use a consensus-backed leader for writes. A quorum confirms updates, while reads can be strongly consistent or intentionally stale depending on the feature. Nodes need health checks, snapshots, replayable logs, and automated replacement. During a network partition, I would prioritize consistency for security and routing metadata rather than accepting conflicting writes. I would also test failover, restore procedures, and rolling schema migrations before production rollout. Discuss replication, leader election, quorum reads and writes, consensus, failure detection, stale reads, partition behavior, recovery, schema migration, backups, and the availability consistency trade-off for configuration metadata. Question 7. What techniques would you use to make a distributed service resilient to partial failures? Partial failure means some dependencies fail while the overall system remains alive. I use bounded timeouts, retries only for safe operations, exponential backoff with jitter, and circuit breakers to stop cascading overload. Bulkheads isolate tenants or workloads, while idempotency makes retries safe. Where appropriate, the service returns cached or degraded results instead of blocking indefinitely. I validate these mechanisms with dependency failure tests and monitor error budgets, latency, saturation, and recovery time. In your answer, cover timeouts, retries with jitter, circuit breakers, bulkheads, idempotency, fallback behavior, health checks, dependency isolation, telemetry, and chaos or failure injection testing. Question 8. How would you secure a multi-tenant observability platform? I would enforce tenant isolation at every layer, not only in the user interface. Authentication identifies the principal, while authorization checks tenant, role, resource, and action before querying or exporting data. Data is encrypted in transit and at rest, secrets use a managed vault, and audit events record administrative access. Query filters must be server-side and tamper-resistant. I would add automated isolation tests, especially negative tests proving one tenant cannot retrieve another tenant's events. Make sure to discuss authentication, authorization, tenant boundaries, least privilege, encryption, secret management, audit logs, input validation, data masking, secure defaults, and testing for cross-tenant data leakage. Question 9. Describe a caching strategy for frequently accessed dashboards or search results. I would cache results only when the query, time range, permissions, and data freshness requirements make a stable cache key possible. A short TTL can reduce repeated dashboard load, while revalidate keeps user latency low. I would prevent stampedes with request coalescing or jittered refreshes. Cache entries must include tenant and authorization context, and sensitive data needs careful handling. Hit rate, eviction rate, staleness, and origin load determine whether caching is worthwhile. Cover cache keys, TTLs, invalidation, freshness requirements, negative caching, eviction policies, stampede prevention, tenant isolation, cache consistency, and metrics showing hit rate, latency, and memory pressure. Question 10. How would you evolve an API used by many internal and external clients? I prefer backward compatible, additive changes, new optional fields, new endpoints, and tolerant readers. For breaking behavior, I would introduce a versioned contract, publish migration guidance, and run both versions during a defined deprecation period. Consumer-driven contract tests catch accidental changes, while usage telemetry identifies clients that still depend on old behavior. I would document error semantics and pagination clearly. Compatibility is not just syntax, it includes performance, authorization, and operational expectations. Be sure to mention backward compatibility, semantic versioning, additive changes, contract testing, deprecation timelines, feature flags, validation, documentation, telemetry, and communication with affected consumers. Question 11. How would you investigate a production latency regression? I would compare current P50, P95, and P99 latency with the baseline, then correlate the regression with deployments, traffic shape, configuration, and dependency metrics. Distributed traces help identify whether time is spent in application code, storage, queues, or network calls. I would first mitigate safely, perhaps by rollback, traffic reduction, or disabling a feature. After recovery, I would reproduce the issue, add a regression test, and document the root cause rather than stopping at the symptom. Focus on establishing the baseline, narrowing the time window, comparing deployments, examining percentiles, traces, logs, saturation, dependency health, recent configuration changes, rollback criteria, and permanent corrective action. Question 12. What is your approach to testing a distributed event processing system? I layer tests. Unit tests cover parsing, routing, and transformation rules. Integration tests exercise queues, storage, and authentication. Contract tests protect service boundaries. I add property-based tests for malformed and unusual events, then run load tests against realistic distributions. Fault injection scenarios cover retries, duplicate delivery, reordered events, node loss, and recovery. Deterministic fixtures make failures reproducible. End-to-end tests verify user-visible search results, while dashboards track both correctness and performance. Discuss unit, integration, contract, property-based, load, fault injection, replay, ordering, duplicate, recovery, and end-to-end tests, along with deterministic fixtures and meaningful correctness and performance assertions. Question 13. How would you choose between a relational database, key-value store, and document database? I start with access patterns rather than database popularity. A relational database fits transactions, constraints, joins, and evolving business relationships. A key-value store works well for predictable lookups at massive scale with simple values. A document database suits aggregates whose fields evolve together and are usually read as a unit. I evaluate consistency, partitioning, indexes, backup, and operational maturity before deciding. Polyglot persistence can be valid, but each additional data store increases maintenance and failure modes. In your answer, compare access patterns, consistency, transactions, schema flexibility, indexing, scale, operational complexity, query relationships, failure behavior, and whether the chosen model matches real product requirements. Question 14. How would you prevent a noisy customer or workload from affecting other tenants? I would enforce quotas and rate limits at ingestion, query, and export boundaries, using tenant-aware accounting. Fair scheduling prevents one customer's large searches from monopolizing workers, while separate resource pools or partitions isolate especially sensitive workloads. Admission control should reject or defer work predictably instead of exhausting shared memory. I would expose usage metrics and clear limit errors, then autoscale from demand. The design must protect reliability without making legitimate bursts unnecessarily painful. Make sure to cover quotas, rate limiting, admission control, fair scheduling, resource pools, partitioning, priority policies, monitoring, tenant-aware autoscaling, and communicating behavior when limits are reached. Question 15. Tell me about a time you disagreed with a technical decision. On one project, I disagreed with introducing a new data store before validating the workload. I shared measurements showing our existing database handled expected traffic and proposed a benchmark plus a reversible abstraction. The team agreed to run the benchmark, which exposed that the real bottleneck was inefficient pagination. We fixed that first and postponed the migration. I supported the decision once evidence was available, and I learned to frame disagreement around shared goals rather than personal preference. Prepare a concise star story showing respectful disagreement, evidence-based reasoning, customer or reliability impact, collaboration, compromise, measurable outcome, and what you learned regardless of the final decision. Question 16. How would you prioritize reliability work against feature development? I quantify reliability work through customer impact, incident frequency, recovery time, and error budget consumption. If a service repeatedly violates its objective, Feature delivery should slow while we remove the dominant risks. I would break remediation into incremental milestones, such as eliminating one failure mode or improving rollback time, and attach measurable outcomes. Product and engineering leaders need transparent trade-offs. Reliability is not unlimited perfection, it is a deliberate investment aligned with user expectations and business consequences. Discuss customer impact, error budgets, incident trends, risk reduction, opportunity cost, measurable objectives, incremental remediation, stakeholder communication, and using data rather than treating reliability as an abstract preference. Question 17. How would you design a safe deployment strategy for a critical backend service? I would build an immutable artifact, run automated unit, integration, security, and compatibility tests, then deploy to a small canary slice. Health checks should include error rate, latency, saturation, and business-level correctness. Progressive rollout limits blast radius, while feature flags separate code deployment from behavior activation. Database changes must support old and new versions during transition. Rollback should be automated and rehearsed, and irreversible migrations require backups, staged changes, and a recovery plan. Cover automated testing, artifact immutability, progressive rollout, canaries, feature flags, health metrics, rollback, database compatibility, observability, approval policies, and handling changes that cannot be instantly reversed. Question 18. How would you design an alerting system that avoids overwhelming engineers? I would alert on user-impacting symptoms and fast error budget burn rather than every low-level metric fluctuation. Related events should be grouped, deduplicated, and assigned to an owning team with severity and escalation rules. Informational signals belong in dashboards, not pages. Each alert needs a runbook and a clear action. I would review false positives, missed incidents, and responder feedback regularly. Good alerting reduces cognitive load while still detecting meaningful degradation early. Be sure to mention actionable symptoms, service-level objectives, multi-window burn rates, deduplication, grouping, severity, ownership, suppression, escalation, runbooks, and reviewing alert quality after incidents. Question 19. How would you improve the performance of a multi-threaded component? I would profile first to distinguish CPU time, blocking, allocation, and lock contention. Then I might reduce shared state, narrow lock scope, use immutable data, partition work, or replace a contended queue with per-worker structures. Thread pool size should reflect CPU and I/O characteristics, not an arbitrary multiplier. I would run repeatable benchmarks under realistic concurrency and use race detectors or stress tests to protect correctness. Faster code that introduces non-deterministic corruption is not an optimization. Focus on profiling before optimization, contention, lock granularity, data ownership, thread pools, queuing, CPU versus I/O behavior, memory visibility, race detection, benchmarks, and preserving correctness. Question 20. Why do you want to work at Splunk, and how would you contribute as a software engineer? I'm interested in Splunk because its products turn complex machine data into decisions that improve reliability and security. That mission combines distributed systems, search, data quality, and strong customer impact. I would contribute through disciplined design, clear operational ownership, and pragmatic iteration. In previous work, I improved a high-volume pipeline by measuring bottlenecks, adding safer retries, and strengthening monitoring. I enjoy collaborating across teams, learning unfamiliar systems quickly, and building software that remains dependable under pressure. Prepare to connect Splunk's observability and security mission with your experience, distributed systems interests, customer impact, collaboration style, technical strengths, and a specific example demonstrating ownership and learning. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.